morning, everyone. Hope you're doing well today. Good morning to you too. Actually, a pretty nice day out today. Started out kind of cloudy and then it all cleared up. Looks nice out there. Well, this week, or today, we're going to wrap up the first half of the semester. We're going to do a demonstration or a discussion and demonstration about how passwords get stored on computer systems and how they, like when people break into computer systems, how do they actually get the passwords out of them? And then that'll wrap up, like I said, the first half of the semester. By the end of the week, I should have a survey, something for you to fill out. Kind of just serves as a check to see how you're doing in this semester so far. Just make sure you're kind of caught up with the assignments, get some feedback from you about how the semester is going, and then we'll move on to the next half of the semester. We'll be learning about, what are some of the topics? Sets, counting problems, or counting like combinations and permutations. We'll do some problem sets based upon that. And then we'll get into graphs, some of the algorithms involved in graphs like shortest path and spanning tree. And then we'll move into finite state machines, and we'll learn about compilers and programming languages. And then that'll wrap up the rest of the semester. Do we have any questions before we begin? Permutations, combinations, sounds like statistics. It is kind of. I didn't mention that we will also, after doing combinations and permutations, move into a week or two where we talk about a discrete probability, so that is kind of related to statistics, but we'll use how spam filters work as something to learn about as we're learning about these statistics. So I always try to tie in what we're learning with something that's kind of computer science related, practical information. It's not just this abstract mathy stuff that we're talking about. So let's get started here. So I have some questions for you. So we're going to be talking about hashing today. And I kind of mentioned some of the names of these common hashing algorithms last time, like MD5, SHA-256 and 512 and bcrypt. And each one of those hashing algorithms takes data that you feed into it and then essentially distills it down, boils it down to a fixed size, a fixed amount of information. And so let me start you out with these questions here. Let's say you have an organization, a business, and the business says that all passwords have to be exactly 8 letters long. I know that's a silly restriction, but let's just say that's what it is. How many possible passwords are there? If the passwords are exactly 8 letters long, uppercase and lowercase, how many possible passwords are there, assuming that people just pick kind of random passwords? How do we figure out that answer? What's the calculation we need to do?
8 to the 56.
8 to the what? What did you say?
52. 8 to the 56.
Oh, the other way around. So 52, which is the number of letters in uppercase and lowercase.
Oh, today.
Yeah, raised to the 8th power, because you've got 52 possible letters you could put in the first position, 52 in the next, 52 in the next. And you multiply all those together. So 52 to the 8th is, I'm using my computer as a calculator here, about 53 trillion. Well, it's 53.5 times, I think 10 to the, try counting up these numbers here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Actually, a better way to write that would be 5.35 times 10 to the 10th. And let me just check to make sure I got that number right in terms of the scientific notation. Oh, let's see what. Let me see. What day is it? Let me look back at my notes here. Well, I think I got that right. About 53 trillion combinations. And let's say also that you decide to go up to just letters and digits. So including the letters, you've also got the digits. Then how many possibilities are there?
62 to the 8.
Yeah. 62 to the 8th, which is, let me try that out here. 62 to the 8th power. We're looking at about 218 trillion. Which is 2.18 times 10 to the probably 11th. So it seems like a lot, but, you know, really, an average computer these days could go through all of those combinations, you know, pretty quickly. I mean, not like instantaneously, but it might take a few hours to work through them. And so maybe as the, you know, the IT administrator, you decide to bring in a security consultant, and they recommend that you go up to 9 letters. So rather than adding complexity to the password by adding digits onto it, they recommend you go up to 9 letters instead. So don't use digits, just use more letters. And the question is, how many possibilities are there? So we're going back to letters, uppercase and lowercase, but 9 of them. And so now we're looking at about 2.8 quadrillion, or 2.8 times 10 to the 15th. So that may go against your intuition a little bit, that if you have a choice between making a password more complex by adding more symbols or more characters that you can use, versus just making the password longer, it's almost always a better bet to just make them longer, even if the complexity itself doesn't change. There's, of course, an XKCD comic for just about all of these things. Let me bring it up here. This one's been running around for a few years. You know, typically you run to a website or some kind of service where you have to pick a password, and sometimes they recommend you just pick like a really complicated password, like, you know, throw in some letters, throw in some numbers, some symbols, has to be a minimum length, And what you usually end up with is just this incomprehensible gibberish that's really hard to remember, but does meet their complexity requirements. And the problem with using all of these symbols in there is that you're really not adding a whole lot of complexity to it. I mean, when you switch from, or when you, what am I trying to say? If you have only lowercase letters and then you add uppercase letters to it, you're really only adding about one extra bit of information to that. I mean, it's lowercases versus uppercase. So it's just one extra bit of information to dictate whether it's a lowercase or uppercase letters. And when you throw numbers in there as well, you're not adding more than about 1 or 2 bits of information. So really, when you increase the complexity, you're not adding a whole lot to the extra amount of information that is in the password. Sure, you're making it a little bit harder for people to guess what the password is, but you're also making it a whole lot harder for you to remember what that password is. So if you pick a typical, what do we got here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 character password, you've only got about roughly 28 bits of actual information in there. And it would take about 3 days for a computer, and this was back about 5 or 6 years ago. It would take about 3 days for a computer to just whip through all of those possible passwords and eventually stumble across the password that you got. So these passwords are hard to remember and relatively easy for computers to just try all the possibilities and eventually guess it. So the recommendation here is just pick like 4 words that for yourself are easy to remember. So we're just sticking with letters and spaces. 4 words that are easy for you to remember, stick them together, and now you've got about 44 bits of information. And it would take about 500 years for a computer to stumble across the correct set of words. And if you pick the words carefully, they might make perfect sense to you, even though they appear random to someone else, and that makes the password easy to remember. So it's almost always a better bet to make the passwords longer versus adding more complexity. However, you still these days run across websites all the time that just insist that you pick really complex passwords. Of course, actually, I think the best of both worlds is to have something like a password manager on your computer. Pick random passwords for you that are nice and complex and nice and long, and then just store them away in a encrypted database on your computer so that every time you go and visit that website, it just fills in the form for you. My phone does that for me. My computer does that for me. It's really great because I don't have to remember these long, complex passwords anymore. And every time I sign up for a new web service, it just picks a really long, complicated password for me to use. Is anybody else here using a password manager?
Yeah, I use one called Bitwarden.
It works pretty well.
It's actually a self-hosted one.
Okay. And does it sync across all your devices? So all your devices.
It has there's an app, there's a Chrome extension. It's really nice actually.
Yeah.
And there's a bunch of customization that comes with it.
I think Apple device, on Apple device have the password manager in the software, in the operating system itself. So
yeah,
really no need.
Yeah, that's pretty much the one that I use.
I just don't like how they don't have like a Windows extension for that, you know?
So Windows doesn't yet have something that's just built in?
It's not like compatible with the iCloud keychain.
Oh, he mean that if you use the Apple Manager, then it won't work with Windows and other operating system. So a third-party software is the best.
I think they tried to make an extension a while ago. I'm not sure why they didn't, but something went wrong with it and they like took it off the Chrome store.
So they were working on it, but
I think there was some security flaw.
A good cross-platform one to use, and again, I I use this one, but like I have no tie to the company at all. It's called 1Password, and that has Windows clients and Mac clients and iOS, and and it syncs across all your devices. So if you're looking for a nice cross-platform one, that one works pretty well. But for me, just the built-in one works seamlessly almost all across all devices, and even the apps themselves, the individual Facebook app or Spotify app know how to use that password manager as well, so we can just fill in those passwords too. So I really like using a password manager. On YouTube, Dimitri says, pen and paper, my password manager. As long as you can pick good, hard to guess passwords, but easy to remember for yourself or easy to look up, I think that works pretty well. It's just that for me, I have hundreds of passwords, and so it's just easier to have my device memorize them for me.
You lost the paper?
Oh, what happens if you lose the paper? Yeah, that's a good point. So I wanted to give you a little bit of a demonstration about how passwords get stored on a computer system. Like when you go to a website and they ask you to enter a password, you'll usually pick a username, maybe enter your email address, and then pick a password. And then they've got to store that away somewhere so that the next time you log in, they can check to make sure that you got your password correct. Now, first of all, you might ask, what is a good way to store passwords? And so clearly a good way to do it is not to just store it in plain text. Like you shouldn't just have a file sitting on the computer, the server, that has your username and then your password right next to it. I mean, it would be easy to look up passwords that way. When you type in your username and password on a subsequent login, all it has to do is just scan through that file, locate your username. Right next to it on that same line will be the password, and then it just checks to make sure, does the password stored in their database match the password that you just typed in? If it does, it lets you in. But obviously, if somebody were to break into that computer system and obtain that file, not only would they have your password, they would have everyone else's password, including probably the administrator of the server. And so that would not be a good way to do it. And so you also might think, well, what about encrypting the password? Why don't we store the username and the password, but we'll encrypt it using something like AES or RSA or something like that? That would work pretty well. Then when you log in on a subsequent login, it just scans for your username. Now the username itself is probably not encrypted. It's just there in plain text. When it finds that username, right next to it is the encrypted password, but now it has to decrypt it. And since this is a computer and the whole login process is automated, there's not somebody sitting there at the keyboard typing in the secret code that's used to unlock the password. That has to be stored on the computer system somewhere. So it could then read in a file that contains the secret key needed to unlock the password. But if someone were to obtain that file, then they would be able to decrypt all the passwords. And then it's just not any better than having the passwords in plain text. So encryption is not the best way to do it either. So instead, websites and most services use use hashing, basically, to store passwords. So the way a hash works conceptually is think about like a coffee grinder, right? You want to make a cup of coffee in the morning, and your cup of coffee needs only a tablespoon of coffee grounds in order to work. But all you have are whole coffee beans. You have a whole jar full of them. So what you're going to do is you're going to take a scoop of coffee beans and you're going to put them into your coffee grinder. You're going to press that button, and shake the whole thing up, and it's going to whirl around. Those blades are going to whirl around and chop up those coffee beans into a fine coffee ground. And then you're going to take a spoonful of that, scoop it out of the coffee grinder, put it into your cup, and then brew your coffee. Now, is it possible to take that scoop of coffee grounds and reverse it and get back the original coffee beans? Now, forget about the whole physics aspect of it, right, of entropy and stuff like that. Let's imagine you've got a coffee grinder in which you whirl the blades in reverse, and it puts together whatever you put into the coffee grinder. So if you put the coffee grounds back into the grinder and whirl the blades in reverse, it will reassemble the coffee beans. Now, the question is it possible to do that with that scoop of coffee grounds that you have? And the answer is no, you can't do that. I mean, you started with, let's say a cup full of coffee beans, and you put it in the grinder, you ground it up, and then you pulled out just a spoonful of the coffee grounds, and you threw away whatever was still in the coffee grinder. And of course, some of it also just got lost along the way, right? The blades are whirring, the dust is flying, and so some of the coffee grounds just disappear. So there's actually less coffee at the end, coffee beans at the end, than what you started with. And so it's not possible to reconstruct the original beans from the coffee grounds because you've just lost some of them. You threw away what you didn't use, and some of them got lost in the whole process. So it is not possible to reverse it. So it's easy to take the coffee beans and turn them into coffee grounds, but it's near impossible to take the coffee grounds and reverse it back into the beans. And so this is what a hashing algorithm does. And we also saw it with checksums. Checksums do the same thing, but on a much smaller scale. So with a hashing algorithm, the coffee beans represent the data, or maybe the password that the user types in. It then takes that password, the bits that represent the password, it runs an algorithm on it that whirls those bits around, swaps some of the bits, exchanges them, reverses them, inverts them, and then what comes out is a hash, the coffee grounds, with the password bits all mixed up. But along the way, some of the bits got discarded. And so it's not possible to take the resulting hash and turn it back into the original data. Now, passwords are fairly short, but hashes work with data that's much larger. You could throw at it, a megabyte of data, and it would do the same thing. It would take all the bits corresponding to all the bytes inside of that data. It'll whirl them up. It'll, exchange some of them, switch some of them out, throw away some of them, and at the very end, you just take a fixed size amount of bits, you scoop out those bits, and you say, here is the resulting number from this algorithm. The reason why it's called a hash is because it goes back to have you ever had hash for breakfast, right? You take some meat and some potatoes and you chop them all up and you whirl them, you stir them around. That's where the name comes from, right? You're just basically taking whole things and then chopping up into fine little pieces. Right, exactly. Hash browns is exactly where the word comes from. So with these hashing algorithms, you take any data, you put them through this hashing algorithm, and out comes a number. And that number is based upon the original data, but you can't reverse it back. You can't take that number and put it back to the original data. Let me give you some demonstrations of that. So
a hash is almost like a lossy cipher.
Yeah, it's definitely lossy, right? You lose information along the way. And it's not even like you lose a little bit of information, you lose a lot of information. So right here, I've got a file that is the complete works of Shakespeare. It's all of his sonnets and plays, poems. And this file is about 5.5 megabytes. And I think it's sort of an interesting commentary on the technological process that this 5.5 megabytes represents the entire life's work of an author back, what was in the, I don't know what the year was, like the 1500s or something like that, 500 years ago. So for an entire life, he generated just 5.5 million bytes of information. And today, I can generate that much information in 1/100th of a second by taking a picture. So, the amount of data that we produce every day just far exceeds the amount of data that someone back then would have produced over an entire lifetime. Someone says, not so fast. I'm trying to read them. Anyway, so I can take this complete works of Shakespeare and I can run it through one of these hashing algorithms. Let's use something like MD5. So it read in the entire file, put it through this coffee grinder, if you will, and out popped this number. This is represented in hexadecimal, but it is a 128-bit number. And if I run the same file through the same algorithm again, I get the same number. This file is 124,000 lines long. Let's go into that file and let's just make a little tiny change to it. Let's just go to like line 40,000 and let's just change one of these letters. Let's change this A to a B right here. Essentially, I have just changed one bit in this entire file by going from one letter to the next letter up. And then we'll run it through the same hashing algorithm, and we'll see that the number that comes out is like completely different. And that's really one of the beauties of these hashing algorithms, is that when you change just one bit in this entire file, this 5.5 megabyte file, you get a hash that is completely different. I mean, even it bears no resemblance to the original hash. And so this lets you know that something was changed in the file. It does not tell you where in the file, but it just tells you something is different about those two files. You can actually see hashes if you go to a website where you have to download some software. Like let's say you're installing a piece of software for your computer. Many times on these websites, particularly these open source websites, you can go to and download something, some free program. And I'm talking about like spam programs. I'm talking about like something useful, like a password manager or something like that. Sometimes right next to the download link will be one of these hashes. It'll say that the MD5 hash of this file is, and then it gives you the number. The idea is that you'll download the software to your computer, and if you feel really like paranoid about it, you can run the MD5 or the SHA algorithm on the file you just downloaded and see if the hash that you got matches what's on the website. If they're different, then you know that something got corrupted along the way. You should probably download the installer again. If they match, then you know, or you can be pretty confident that the files actually do match each other. Okay, let's go make another change to this file. Let's go to a different line. Let's say 80,000. And, I'll just change one of the letters in there. And then run the hash again. And we can see we get a completely different number. Again, we don't know what has changed, but we just know that something is different. So this should give you an idea now about how passwords get verified on a website. The first time you create a username and password, it takes your password, it hashes it, and then it stores your username in plain text and the hash right next to it in a file or a database. The next time you log in, you enter your username and password. It scans through that file looking for the username. Right next to it will be the hash that was inputted or saved there the first time you created your account. So now you've got your password that you just entered. It will hash that password and then see if they match. So we've got the hash that was stored when you created your account, and then we've got the hash from this subsequent login. If they match, then it means the original password's matched. And if they're different, we know that something's different about the password that the user entered, and we should reject the login. So the system does not know what your password is. In fact, that information has been lost. That's why when you click on that link that says, I forgot my password, The best that these websites can do is say, all we can do is change it. We can't tell you what your original password was. We have no idea what it was, but we can let you change it to something else. And if you ever do run across a website that is able to tell you what your password is, like, I forgot my password and it says, oh, it was aardvark, then that means that they are not storing the passwords as hashes or encrypted or anything like that. They're just storing it in plain text and are able to tell you what it is. So I would actually be very suspicious of a website like that, because it means that your password is somehow recoverable. And it means that if somebody breaks into the system and obtains the database of usernames and passwords, they would be able to recover the passwords as well. Any questions so far? So you can generate your own hashes. You can just use, something like, you can actually do it on Jupyter. Let's go ahead and try that out. See if I can remember how to do this. You can say from hashlib import star. Good. And then now we can type in MD5, and then we can type in a string here. Now the string that you type in has to be a byte string. So we have to put a B in front of that, and then put our quote marks. And let's just put hello inside of there. And what we get back is what it calls a hash object. So we need to convert that into hexadecimal so that we can see it as a number. So the way you do that is you put hex digest method on the end, and now we get back the actual hash. So MD5 byte string, let's put in something else. What did I, let's put in hello, but I'll just change the O to a P. And you can see the hash that you get out is completely different. Now there are other hashing algorithms. There's SHA-256. And that one produces a 256-bit number, so it's twice as long as an MD5, but you can see that they bear no resemblance to each other because they are a completely different algorithm. The way it mixes up the bits is totally different. So the question is there any detectable pattern to hash codes? That's actually a very good question. So an ideal hash algorithm should produce output that is not easily predictable for a given input. So if you give me an input, I should not be able to very easily predict what the output is going to be. In other words, the output appears to be random. A good hashing algorithm should be difficult to reverse, so I shouldn't be able to take the output hash and figure out what the original input was. And the output should also be evenly distributed. If I was to plot how often each individual hash value came up over a span of many, many documents, then I should see those bars on that histogram be, roughly about the same height. There shouldn't be big gaps between the bars. There shouldn't be any bars that are higher, much higher than others, because that would give an attacker potentially a little bit of a clue about what the original text could be, if there was some kind of information in the hash itself. So the hash output should appear to be random. It should be evenly distributed across all possible values, and it should be difficult to reverse. Actually, it should be almost impossible to reverse. So when a mathematician or a computer scientist says difficult, they don't usually mean just like a little more difficult. They mean a lot more difficult. Like there are easy problems and there are hard problems. Easy problems are like, arithmetic, and hard problems are ones where you'd have to grind away at it for years or decades or centuries in order to figure out the solution. So easy means can be done fairly quickly, and hard means takes a long, long, long time to do. It's almost like there's not much in between, right? There's easy and there's hard. So there should not be any predictable pattern to a hash code, even if you had a whole list of them. They should all appear to be random and separate from each other. Let's try some of these other algorithms. Let's try 512. So this is a related one. You know, it's basically the same algorithm. It produces 256 bits of output rather than 500. It produces 512 bits instead of 256 bits. But its the resulting number is twice as long, but still actually bears no resemblance to the 256. So even when the hash is really long and I just change one of the letters, you can see that the resulting hash is completely different. What's the probability if two different texts have the same hash? Well, we can figure that out. What's the probability if two documents or two inputs have the same hash? So assuming the hashes are essentially random or evenly distributed, it means that it's unlikely that two documents will have the same hash. This is very unlikely. It's not impossible. There are a limited number of hashes. It is a huge number, but there is a finite and fixed number of possible hashes. So for MD5, there are 128 bits. And therefore, there are 2 to the 128th number of possible MD5 hashes. So that means the probability that two different inputs will have the same hash is about 1 in 2 to the 128th. And if you're using one of the hashes that have a larger number of bits, like SHA-256, then the answer is 1 in approximately 2 to the 256. So it's extremely unlikely, very unlikely, that two inputs will have the same hash. But even though 2 to the 128th or 2 to the 256 is a really big number, it's still smaller than the total number of possible inputs there are. I mean, 2 to the 128th here, which is MD5, is only a 32-byte number. 128 bits, so it's 32 digits. Well, most documents are longer than 32 digits or 32 bytes. And by most, I mean like there's the complete works of Shakespeare. That one is 5.5 million bytes. So most documents are longer than a hash, which means there must be other documents out there that have the same hash. There must be. It's just it's a matter of numbers here, right? There are a huge number of documents, a huge number of hashes. This is the number of MD5 hashes, right? It's this huge number. But that is eclipsed by the sheer total number of documents that are possible. I mean, think about all the possible documents that have 5.5 million bytes in them. Right? It's just an insane number. And so there must be at least two documents out there, two inputs out there that have the same hash. The trick is just finding them. there must be 2 passwords that have the same hash. But it'd be really difficult to find out what they are because they appear to be random. So it's 1 in 2 to the 128th. It's a really small chance, but it's not 0. So how would you go about cracking these passwords? If you broke into a computer system and you obtained their database that has usernames and hashed passwords next to it, how would you go about actually cracking those things? And the answer is you just have to do what's called brute force. Brute force means try all possibilities and see which ones happen to work. I mean, you could literally start with the password A, you know, a whole bunch of A's, and then just cycle through all the possible passwords, working your way through B, C, D, and then once you got to Z on the very last letter, then you roll back to A and increment the next letter to B. So there would be a huge number of passwords to try, and as we saw earlier, if it was 8 letters long, you've got like trillions of passwords to try, but that wouldn't take actually that long to do on a modern computer. So it would be easy enough to write a program to just do brute force, but actually hackers know that humans don't pick random passwords. If you were to just, you know, go and ask the average person, tell me a password that you use on a website, chances are it's not going to be just some random jumble of letters and symbols. It's going to be something like a word, or a word with a couple of letters stuck on. If you don't use a password manager, how do you typically choose a password, right? You pick a word or a phrase, a short phrase that makes sense to you, and then if it requires some complexity, like digits or symbols, what do? I mean, really, what do you do, right? You stick a 1 on the end, right? Or you change one of the letters, change an O to a 0, or you put a $sign at the beginning, or somewhere in the middle, right? It's actually a fairly limited number of things that people do to, pick a password. And so the hackers know this. Hackers know that if you want to break someone's password, especially if you've obtained a whole list of hashed passwords, you don't really have to do brute force. You can just do what's called a dictionary attack. Just try words in a dictionary, and eventually you'll hit some of them, just because people choose dictionary words. But you can actually do one better than that. Remember, when I hashed the word hello, actually, let me go ahead and do it here. When I hash the word hello, I always get this number as the output. Doesn't matter how many times I hash the word hello, I will always get a number that starts with 5D41402ABC. I will always get that. And it doesn't even matter what computer I do it on. Every single computer does the MD5 algorithm exactly the same way, and so they always produce the exact same hash. So what some people have done is they've taken millions or billions of common words, or common phrases, or common passwords, and then they just hashed all of them. And so they got this database that contains a password, a potential password, and its hash. So if you want to crack a hash, if you've obtained a hash, all you have to do is just look in this giant file, look for that hash, and then right next to it will be the password. So you can go to a website like hashes.com or CrackStation, and you can do exactly that. You can just paste in a hash that you've obtained, and they'll check to see, is that hash one that they already know about? Let's go ahead and try it out. let's take our hello hash right here. I'm going to just paste it into CrackStation. I'm going to check I'm not a robot. And then bingo, we got it. Here's the hash I typed in, and they said the answer is hello. So they didn't actually crack the hash. They didn't reverse it. They just looked in a giant database. Let's try some other things. Let's come up with some other, like, think of a password that someone might use. Obviously it's not just going to be a random jumble of letters and numbers, but let's pick something like I don't know, aardvarks 45. And I'm going to go to CrackStation and paste that in. It says you can paste it up to 20. So let's go ahead and put in some more.
You can just use the word password. I believe that a lot of people use.
Just do the word password, okay? How about some others? Tell me one of your passwords. No, not serious. Tell me a password that you think someone might pick.
128.
1, 2, 3, 4, 5, 6, 7, 8. And then I'm even going to pick kind of like a phrase. Let's do hello world. And then maybe let's also try hello world with some capital letters and an exclamation mark and a space. No, someone said let's do QWERTY, all right? Okay, we've got 6 of them to do, and I'm going to copy these, and we're also going to paste them into hashes.com, which is a same idea but just different organization. And let's go ahead and click on I'm not a robot, and it got all of them. So all of those hashes were known to CrackStation ahead of time. And how about hashes.com? Oh, let's try that again. N2 GETPR. There we go. And it got all of those too. So both CrackStation and hashes.com knew all of these hashes. So the way CrackStation works, we can read about it down here, is what they did was they took every word out of Wikipedia, along with every password list they could get their hands on. It applied some intelligent word mangling, which is things like put a number on the end, change one of the letters to a number, and then made a 15 billion entry lookup table that is 190 gigabytes long. So they took 15 billion possible passwords and then hashed all of them, and then just made this giant file that contains a hash along with the plain text password. You can download those files right here. It says you can download them right here. You click on that, go and download 190 gigabytes of hashed passwords. Hashes.com kind of works the similar way. So you see how easy it is if you pick, commonly used passwords on your websites. As chances are, someone has already seen this password or has at least figured out, like, this could potentially be a password that someone might use, and all they've done is just hashed it and then stored away those hashes along with the plain text password. How about password with $2 signs? I got that one too. So even throwing in a couple of symbols means that somebody's already figured that out ahead of time and has already hashed that. Now, you might occasionally stumble across a hash that it doesn't know. Let's try one that's like really complicated. Let's do hello world again. But let's change maybe, let's put a slash in there instead of a space. Let's put a 1 instead of an L. Let's change this E to a 3. And then let's put in, I don't know, let's put a symbol on the front. Let's put an ampersand on the front. So a really nice complicated one. And let's throw it in there. And it does not know that one. So that's not one that it had predicted in the beforehand. If you try to check your own strong password, do they put that in their database? Well, the thing is, like, all you've given them is a hash. You haven't told them what the plain text is. But I think there is a way on some of these sites to go and submit your own passwords to this, or at least submit words to use. So a place where you could type in some plain text passwords, they'll go ahead and hash it and then store it away in their database. By the way, you can check to see if a password that you normally use has been included in one of these password leaks that you hear about like every week. If you go to a website like Have I Been Pwned, which is a legitimate website. This is run by a security researcher, so it's totally safe actually to type stuff into this password, this website. You can put in your email address here, and it'll tell you whether or not that email address has shown up in one of these password leaks. And oh no, I've been pwned. This email address has shown up in 2 data breaches, the Discuss data breach and Gravatar. I knew about the Discuss one. This Gravatar one is new to me. So what does that mean? It means that somebody out there potentially has obtained at least a hash of your password that were used on these 2 websites, and maybe even knows what that password is because they've run it through a website like CrackStation or hashes.com, especially if you use a common password, and they probably already know your password at this point. And then there's also a place where you can type in a password that you use, and it'll tell you whether that password has been used in or seen in a data breach. So if I type in this one here, this is one of my very oldest passwords. I don't use this one anymore, but it has been seen in 13 data breaches. And then there's this one here, and that one has never been seen. So that one's still safe to use, at least for now. And then there's this slightly longer one, and that one also hasn't been used. So you can try out this website and see whether the passwords you are currently using on some of your websites or services have been included in a data breach or not. Yeah, and so Max brings up an important thing here, which is a lot of people use the same passwords on different websites. That actually happened to me. I was, I loaded up Netflix on my television, and I saw that there were a bunch of movies on there that I had never watched. Right? They were in French. Right? I never watched French movies because I don't speak French. But there they were on my account, and so I called up Netflix, and they said, well, it looks like somebody has broken into your account, and they know your password. So, the only thing we can do at this point is basically just reset your account, right? We'll just clear it all out. Actually, we'll just delete your account and you just go create a new one. And, I said, oh, that's fine. The worst part of it was I lost all my recommendations. It's all my complete Netflix history was just gone at that point. I was a little sad about that, but not too heartbroken. But then I started thinking about how would they have obtained my Netflix password? And I realized that Netflix itself had not been broken into. It was the fact that I used that password on other websites. And that particular combination of username and password was used on the Adobe website. I had set that up account many years ago, and Adobe had been broken into some years before. And the hackers cracked the password on the Adobe website, and then were able to just try out that username, that email address, and password combination on other common websites, and were able to get into that as well. So I had long since changed the password on the Adobe website because I got alerted, within days of that happening. But that didn't stop the fact that the hackers had already obtained that username and password combination and were trying it on different websites. That Adobe break-in or breach, in fact, was one of a case of how not to store passwords. So the problem there with Adobe was they did properly take your password and hash it. That was the good part. The problem was they took your security questions, right? Do you drink Coke or Pepsi? Or, what was the name of your first animal, pet, right? They put the answers to those questions in plain text right next to the password, the hashed password. And so the hackers just look at the answers to these security questions, and they can kind of figure out what your password was. It could be because sometimes the answers to the, actually it was not necessarily the security question, it was like a password hint. If we ever ask you, if you forget what your password is, we'll ask you these questions, and that'll remind you what your password was. And so you might have looked at, the animal's name was, Muffy, and, your age was 37, and they would just stick those together and just guess what your password was. All right? So that was a terrible way to do it. So Adobe had the right idea. They hashed your passwords, but then they just stored the answers to the password hints in plain text. And so the hackers were able to figure them out pretty easily from that. How about hashing the password 2 times? That is actually a good technique, is to take the hash that comes out and just run it through the hashing algorithm again. You don't get a hash that's more random or less predictable than what you had before, but now the key becomes for someone trying to crack the password of knowing how many times it's been hashed. So if they can't guess correctly that it's been hashed twice, then after they try their potential password and hash it, they'll get a hash that's different from the one they're trying to crack. And so they won't know to hash it again. Some websites go a step further. They don't hash it 2 times. They don't hash it 10 times. They might hash it 500 times. So they run it through the same algorithm 500 times. And then that very last hash is the one they store away. And so in order to be able to verify someone's password in the future, they have to take your password, hash it 500 times, and then match what's in their file. So that is actually a legitimate technique that's used. But again, if the hackers then obtain the source code to your website and are able to see how many times it gets hashed, then you're back to square one. Okay, so if you got websites like hashes.com and what was it, CrackStation, for cracking passwords where the hash is already known in advance. But how could you crack a password if those websites don't have the hash? Well, then you have to resort to brute force. There you have to resort to just, trying all possible combinations. And you could write a program to do this, but it's usually better to use a program that someone else has already written. So you can go to a website like hashcat.net, and you can download what they call the Advanced Password Recovery Program. but we all know what this is used for. So you can download this for Windows and Linux systems, and I have that one all ready to go over here. So hashcat is a really nifty program. It does brute force and dictionary attacks on a hash, and it does it very, very quickly because the code is highly optimized for doing exactly this job. And in fact, if the computer you're running it on has access to a GPU, a video card, like an NVIDIA video card or an AMD video card, or even the discrete, or the built-in video, like, you know, in your CPU, like Intel embedded video, it will use that, and it will use all the independent processors that are on that GPU to help it solve this problem. You know, a typical GPU like an an RTX 2080 you can get might have a couple hundred independent, or even a couple thousand independent little processors, each of which could be set on this task of trying to crack the password. So you might, let's say, divide up a dictionary or a possible set of possible passwords among your individual processors and say, just go at it. Try all the possible combinations in the range of passwords you're going to try, and just see which one of them actually hits it. So this computer that I'm running hashcat on has a server quality GPU on it. It's not designed for putting video games on a screen. In fact, there's no screen at all attached to this computer. It is just there for doing computations. Researchers and scientists use it for doing things like rendering 3D animation or for doing artificial intelligence, but we're going to use it to crack passwords. So this is an RTX 6000 GPU. It has 4,600 compute cores on it. And so the first thing I'm going to do is just see how fast does this thing run. So I'm going to run hashcat in benchmark mode, and it's going to see how many MD5 hashes it can do per second. So M0 means run in mode 0, which is to do MD5 hashes. So here it's just going to crank through as many MD5 algorithms as it can, as quickly as it can, without trying to crack any passwords at all. And what it's going to come up with here is it did about 55 billion hashes per second. 55 billion hashes per second. So it set all 4,600 independent processors on this task, and it said just run MD5 as fast as you can, and it came up with 55 billion hashes per second. So we're going to have that GPU try to crack a password. Let's try something like let's try having it do password, right? Let's say we didn't know what this hash was, and so we're just going to have it try it. So we'll say hashcat MD5s. Here's the hash we want to crack, and then let's say we know that this is an 8-letter password. So each of these question mark L's represents a letter. So it says pick a letter, followed by another letter, followed by another letter, and another letter, and we're going to do that 8 times. So I think that's 8. 1, 2, 3, 4, 5, 6, 7, 8. And then, oops, I am not doing this correctly. I think I have to put the hash on the end. No, hold on. I'm not remembering right off the top of my head how to do this. So I need to scroll up through the help. Oh, these are, by the way, these are all the hashes this thing knows how to crack, right? We've got MySQL hashes, Oracle, Mac OS, Juniper, Aruba, Cisco, AIX, WPA, those wireless password, scrypt, SHA-256, right? So we got just tons of hashes this thing knows about. But here I need to scroll way up here to what mode we're running in. Okay, attack mode, that's what we're doing, -A. Sorry, I need to scroll down. Sorry, I hope I'm not making you too we're talking about like seasick watching me scroll up and down. Okay, past all this. Oh, here we go. Attack modes. There we go. Attack mode 3, brute force. Here we go. Okay, so it knows it's going to be an 8-letter password. It's going to try all 8-letter passwords from A to Z, and it didn't take very long for it to whip through all of those and find it. So how long, I mean, most of that time was just spent kind of like starting up the program. And then once it started doing it, it's just like a fraction of a second. Actually, you can tell us here how long it took. Where is it? Total time. Well, here we go. I mean, I started it at 17:36 and 26 seconds, and 10 seconds later it was done. But that's when I like pressed enter. Most of the time was spent. Oh, here we go. Time actually elapsed less than 1 second. That's what I'm looking for. Okay, what if we made this a 9-character password? Remember we talked about how just adding to the password length makes it more complicated to crack. Let's go ahead and do a 9-character password. Or what's this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is 10. Let's try this one. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this should take it longer to do. Every time we add a letter, we make it 26 times more complicated. And let's get the status here. So actually, it thinks that it's going to take about 1 hour and 42 minutes to do this. So when we do question mark L, it means it could be a lowercase or an uppercase letter. So it's actually 52 times more complicated every time we add a letter on. So this is like 2,600 times longer to do this, and so that's why it's going to take more than an hour. But eventually it'll get through it. Eventually it'll stumble across the answer and it will print it out. So obviously we're not going to be able to finish this in a reasonable amount of time for our demonstration, but it just shows you that it's not very hard to brute force crack a password if you don't know what the password is. You do need to know at least something about the password, right? In this case, we know that it's 10 letters long. If we didn't know that, that would just be more combinations to try. It would just take longer, but eventually we'd be able to do it. I'm going to go ahead and stop this. Now, hashcat also knows how to do what's called a dictionary attack. We can give it a list of candidate passwords to try, and instead of brute forcing it, instead of trying every possible password, it'll just run through that list, hash each one of them, and see if it matches. Now, where do you obtain one of these lists? Where do you obtain a list of possible words? Well, one possible way to get it is just go find one of these open source dictionaries that are out there. Just like pull all those words in and try those. But, you know, that's a good start. But that doesn't necessarily represent passwords that are commonly used by real people. And so there's a file out there called the rocku file, rocku.txt. And you can go and download this file. It's about I think it's about 14 megabytes compressed. And when you uncompress it, it comes out to be about 140 megabytes. So back in 2009, a company named Rocku was hacked, and their password list was obtained. And it says it wouldn't have been too much of a problem if they hadn't stored all of their passwords unencrypted. So the attackers basically just obtained a list of about 14 million passwords that were known to be in use back in 2009. And they published this list, and you can go and download it yourself. You know, look at this list here. And the nice thing about this list is it's not arranged alphabetically. It's arranged in order from most popular down to least popular. And so it turns out that the password 123456 is the most popular password, at least back in 2009, followed shortly by 12345, and then 123456789, and then password itself is fourth on the list. And if you scroll down some more, you can see words like rocku, and then ABC123, and then people's names. And you know, we could scroll through this list. There's about 14 million of them in there. I have downloaded this list. I have it right here. Not that one. And we can scroll through it. And you know, I should warn you that some people pick passwords that I might call colorful. So you might occasionally run across a word in here that, you know, you wouldn't say in public. But nevertheless, if I was to count the number of passwords in there, I've got about 14 million or so. And so these are 14 million passwords that were in use on this website in 2009. Now, security researchers still compile some of these lists every year, and they come up with like the top 10 passwords that people are using. And even, what is this, almost 13 years later, people are still using the same top 10 passwords, right? Occasionally some of the words shift positions in the top 10, but really the most common password these days is still just a sequence of digits. And password itself is in that list, along with things like I love you and so forth. So hackers know that people pick passwords that are in common use. And so you can just try this list against a hash that you're trying to crack. So let's try to crack a password here. Let's come up with another one to use. Let's try this one. Let's try aardvark45. That looks like a good one to try. So we'll say run hashcat. It's an MD5. Here's the hash we're trying to crack, but now we're going to use the rocku file as the source list for our candidate passwords. We're not going to do a brute force where we try every possible password. We'll just try all the ones in this file. And it did not find it. So aardvark45 is not in the rocku file. So you might think, well, that password is probably pretty safe. But it's not, because in addition to this rocku file, it contains about 14 million passwords, there's also what's called a rule file associated with this. And a rule file allows hashcat to apply some common transformations to a given word. So it might put a number on the end, or it might capitalize one of the letters, or switch an I for a 1, right? So common transformations, or reverse the word, right? So there's a rule list that contains 30,000 transformations. So it's going to take all 14 million passwords, transform each one of them in 30,000 ways, and then try all of those. So we'll say run hashcat, mode 0, but now we're going to apply this rules file, and it's called the RockU 30,000 rule. Let's give it our hash and the RockU dictionary. So now there's many more to try, but it found it. It only took a couple of seconds for it to do that. So even though aardrock45 is not in the RockU file, some transformation allows that password to be found fairly quickly. So I have downloaded a couple of files that contain MD5 hashes. In fact, there's one called md5.txt. You can go download this one as well. This contains about 2,100 MD5 hashes. And I don't know where these came from, but let's just see what hashcat can do with this. So we'll give it the rules file, and then md5.txt, and then the RockU file. So it's going to try to crack all 2,000 of these things. And you can see how fast these things roll out of there. Now, eventually this slows down because it found all the low-hanging, easy-to-find ones first. And now it's going on to the harder and harder ones where it has to apply more and more transformations in order to figure out what it is. And even if we let this thing run to completion, it would only get, I think, about half to 2/3 of them. So it'll still leave a significant chunk that it doesn't have a rule for. But still, if this was a password list that we obtained off of some, business or something like that, then this gives us, at least 1,000 or so passwords to start with, right? And a hacker really only needs one to get into a website. And here we've got already 1,000 or so. Let's see, how far do we got? How far are we? We're about 43 seconds from finishing, and we have found so far about 16% of them. Here's a nice password. Look at that one. I guess the trick there is remembering how many A's you typed in. And I have some other password lists. I have one that, so Chegg got broken into. I know none of you use that website, but Chegg got broken into a few years ago. And eHarmony was broken into. I have some of those. And I have 1,800 other MD5s. I have this one called the hardest MD5s to crack. So I've got a whole bunch of these files that contain some hashes. I don't have the usernames associated with them, but at least we can try to crack them. Let's try doing that Chegg one. Now this file is huge. There are millions of entries in this one. So first thing it goes through is it runs through the file. It does things like remove duplicates and maybe sort them so that they're kind of in alphabetical order. Makes it maybe easier to divide up the work. Could I use this to crack like a Bitcoin hash? So Bitcoin hashes are done using SHA-256. And then those are just like random numbers, random digits. So you're not going to be able to use anything like a dictionary attack on this. So there, you're just going to have to grind away using brute force for, 2 to the 256 iterations. And that's going to take like age of the universe to be able to do that. I don't know if it's actually that long. Might be like years and years. You'll consume more compute power than it'll be worth it. All right, so these are Chegg passwords that are rolling out of here. I don't have the usernames for them, but here are the passwords. I'm gonna stop it. So, how many did we do? We didn't even get through, not even 1% of them yet. And you can, sorry, we got through about 8% of them. Here we go. Still plenty to go. And we already had found 1.4 million of them just in the few moments that I was running this. So by the way, how much does a computer like this cost? I'm renting this computer. I'm paying by the hour for this computer. It costs $1.50 an hour to do this. So if you have one of these password lists, if this is like your job, right, just to crack these passwords, and this is a legitimate job, like you can be a security researcher and your task is to go into a business, obtain their password list, and then just see how many passwords you can crack. And that'll give you an idea about how good your security is for your users. It only costs $1.50 an hour to rent one of these machines with this super powerful GPU in it. And this is the low-end machine. You can get a machine that costs about $5 or $6 an hour, and that one has 3 or 4 GPUs in it. So now you can go 3 or 4 times faster. Instead of doing 55 billion per second, you can do 100 billion or 200 billion per second. And it only costs a few dollars. Do hashes typically get generated in the browser and then sent over the internet? No, not usually. Remember, your connection is going to be encrypted anyway, so it just takes the plain text password that you typed in on the form and sends that over the encrypted link to the other side, and then the other side decrypts the data packet and then hashes the password, and that's what gets stored in the database. It's not up to the browser to do that hashing because that means that now the browser knows how that hash is computed. It knows which algorithm is used, and it knows maybe perhaps how many times the hash was run. And so that's not information that the web server wants to let the browser know, because someone could just inspect the JavaScript code and see how it's done. So the best bet there is to encrypt the plain text password, send it over to the other side, decrypt it, and then hash it, store that in the database. What about salting? Some of you brought up this term about salting. So the problem with websites like hashes.com or CrackStation is they know what the hashes are. They've just taken a list of dictionary words or a list of common passwords, hashed all of them, and just stored those hashes away. So anytime anyone sees that hash number, they know what it is. They can just look in this table and find out what the password is. So that's definitely a problem, especially if somebody obtains a password list from a website. They could just look through that password list. Even if they don't know what the passwords are, they could see that maybe 2 of those entries have the same hash, so they know those passwords must be the same. If they crack one, they can crack the other one. So it just lets you know that there are 2 users on the system who have the same password. So what the solution to that is something called salting. That is where you take the user's plain text password. Let's try this out here. So you take a plain text password. Let's say it's just hello. Oops, I need to refresh this and launch my server again because I went idle for too long. Where's my hello? It's right here. Okay, so it takes your plaintext password, it hashes, but in addition to the plaintext password, it appends or prepends onto your password a random sequence of letters or numbers. So in addition to my hello here, I might put on just some random numbers. Like I'll just go on the keyboard here, 7846, right? And I'll hash that. And that's what gets stored in the database, this hash right here. So I took my plain text password and I appended onto it 4 random digits. And that's what gets stored in the password database. So if somebody stumbles across a password list that has all these hashes in there, even though 2 users might have the same password, they will have a different hash because they had a different random number appended to their hash. Okay, so the hello hash will appear to be 2 different hashes in the password file. But now the question is, how do you authenticate the user? When the user types in hello as their password, how does the system know what random numbers were appended onto the end of it so that it can hash that and then produce the correct hash? How does it know that 7846 was appended onto the plaintext password? And so with a salted password file, you need to also store the salt itself. This random set of digits is called the salt. And so what that might look like in a password is the user's name. You know, let's say it's, I don't know, admin or something like that. And then the hash that we came up with, which was, where is it? This one. And then 7846, the salt itself. So when the user logs in, they type in their username, they type in their password, which is hello. The system then goes and looks up their username, looks up the salt, which is sitting right there on the same line, sticks it onto the end of their password, and then hashes it. And then it comes up with this hash, and you see that it matches what is in the file, and so it lets the user in. So, like how secure is that? I mean, you're putting basically that random sequence of characters right in there for, in plain text. And so the answer there is, first thing is, you don't necessarily know where the salt goes. Does it go in the beginning? Does it go in the end? That's not too tricky for someone to figure out. They can try both possibilities and they'll get it. But the real answer there is it's so that you ensure that if the users have the same password, that you won't have the same hash in the file. That's all this is doing, is making it so that the hashes are unique, even if they have the same password. It doesn't add an extra layer of security. It doesn't make the password harder to crack. It just makes it less obvious when 2 users have the same password. So almost all systems now no longer just simply hash the password. They also add onto it something called a salt, which is just a random jumble of letters, and they store the salt away in plain text right next to the hash so that the system can reassemble the plain text password and the salt correctly and then produce the hash that is seen there. So the only purpose there is to make it so that all the hashes are unique in the file and there's no duplicates. That's all it's there for. So if I was to plug this hash into, something like hashes.com, it wouldn't find it because we don't know what the random numbers were that were stuck onto the end. But if we knew what those random numbers were, then we can just append it to the word hello and then come up with that hash and then verify the user. Okay, so it's 11 o'clock now. We need to take a little break. I've thrown a lot of stuff at you, but I hope your takeaway from here is pick better passwords. right? Pick different passwords on different different computer systems, right? Make sure that no two websites or no two services you use have the same password, because these hackers know if they can break the password on one, chances are that password is in use somewhere else. Use a password manager. It'd be a great thing to do. That allows you to generate random passwords for every website, for every service that you use. And even if you don't do that, make your passwords longer. Right? Compose them of multiple words that are easy for you to remember, but hard for someone to guess. I'm glad you got something out of it. The class is very informative, you say, not even in course material, but also everyday problems. Yeah, this is like practical information here, right? Pick better passwords. Right? Go to that Have I Been Pwned website and plug in your password. Plug in your username or your email address and see if you've been included in a data breach. These days, some password managers now do this for you. I've noticed that on 1Password and the one that's built into the Mac operating system, every time I type in a password, or even if I just go into the password manager, it says, you have one or more passwords that have been included in a data breach. You might want to change those. So I've been slowly kind of going through my list and changing some of those passwords. Or use two-factor authentication. You've probably seen that on some websites. You enter your username and password, and then it says something like, we're going to send you a text message with a code, and you need to type that message back to us. Or you use an authenticator app on your phone where there's a code that's like constantly changing every couple of seconds, and you have to enter that code in, and it has to match what the server knows to be your code.
Like the creator of Steam, Gabe Newell, has his username and password out there for the world, and it has two-factor authentication with their like own proprietary system, and no one has been able to get into his.
Because no one can figure out what that code is, right?
Yeah, because it changes every 15 seconds, if I'm not mistaken, and you have to have it on your phone.
Right.
That's registered to your account already, so it's basically impossible to get through.
Yeah.
With
I mean, it's basically a constantly changing password.
Yeah, it's impossible.
Way to think about it.
And also, like, it's not that inconveniencing when it comes to logging in, because it's not like a text message that you're receiving. It's just on the app, and it's always like, I don't know how they do it to the point where it like matches up with the servers, that even if you get like a 2 or 3 second delay, like you're late on it 2 or 3 seconds, it won't let you through at all.
So the way that works is it's basically a random number generator. Each one of those codes is a random number. But as we saw last time, when we talked about random number generators, you know that each number in that sequence generates the next number in the sequence, right? And it's just going around in this giant cycle. If it's a 6-digit code, it's going to take a million times before it finally cycles all the way around and starts that cycle all over again. So your authentication app on your phone knows where in the cycle you are, and it's got a nice accurate clock on it, and the server also has an accurate clock, and it knows where in the cycle you are, because when you first set up two-factor authentication, the server basically says, okay, here's the current code number, and then you type that in on your phone, and now it uses, now they're in sync, right? So you've used both the server and your two-factor authentication app know where in the cycle they are because you just matched up the numbers. Or they might say, here's a code for you to scan on your phone. Same idea. It's basically telling you or telling your app where in the cycle you are. And now every number is used to generate the next number in the sequence. Your garage door opener works the exact same way. You got that clicker, right? You know that when you set up your garage door opener, you have to sync up the garage door receiver and your transmitter in your car. You press a button on the receiver, and then probably a light flashes to let you know it's in pairing mode, and then you go over to the remote in your car and you press the button, and it sends over to the receiver the current number that your transmitter is on, and now they're synced up. And then every time you press the button on your garage door, it generates the garage door transmitter, it generates the next number in the sequence.
If you break that algorithm, you technically could get into it in terms of like what the randomization algorithm that they use.
Yeah, if you know the randomization algorithm, then you can get into it. And you probably also know that if you click the button too many times when you're away from your garage door, it gets out of sync. And then you have to resync them up. So if you like drive away to the supermarket and then press the button on your remote a whole bunch of times, like 10 or 20 times, then your garage door opener remote is now 20 numbers ahead of where the one in your garage is, and they're now out of sync from each other. The one in your garage is able to accommodate that to a certain extent. Since every number generates the next number, it's already like 5 or 6 numbers ahead, right? It knows what the next 5 or 6 numbers are. So if you click that remote and you generate any one of those 5 or 6 numbers, then it'll open the garage door and then resync itself. But if you're too far ahead, then it gets out of sync and it no longer opens the garage door.
I don't know if there's some problem with the Seracoic two-factor authorize, because every time I log in, right, there are 2 options. I get the verification code with the email or the phone via text, but I just choose text and then it's automatic login. No text was sent to me, but it just goes straight to the login.
So no text message gets sent to you, but it lets you in anyway?
Yes.
Oh.
Yes. It's
Well, don't let anyone know about that.
but everyone know.
I've had problems with their two-factor authentication where like it's mostly it's things like I have OneDrive, syncing my files across my computers, and that two-factor authentication just drives it bonkers, right? Because the OneDrive itself is not quite aware that this is happening. And so even after I've authenticated myself, it then a couple days later just forgets about that authentication. I have to do it all over again. So it's just really annoying. And
to the Google, what's it called? Google Drive instead of using OneDrive. It syncs so much better and like it keeps everything.
Well, I'm using OneDrive because I have an account with the school with that.
I gotcha. A lot cheaper.
Yeah. I suspect the problem is because I actually changed my username about 10 years ago. And so I think in the system, it actually has my old username and my new username, and it can't quite reconcile the fact that I'm known by 2 different names. So it doesn't know which one to use sometimes because my username and my email address don't match. The username I type in when it asks for a username is different than when it asks me for my email address. So it's strange, right? So sometimes the login says, enter your email address. And so I enter my email address and then it goes, I can't find you. Or it says, enter your username. And so I enter my username and it says, I can't find you, right? Because sometimes you enter your username and then what it does is it just sticks on the at part of the email address and constructs an email address out of that. And then it says, well, that doesn't match what we have in our system because my email address is different than my username. It's just crazy. And I've talked to the IT folks and they said, there's nothing we can do about that. There's no way in Windows to change someone's username. You can create an alias, you can create a second username for them, but you can't actually change their username. I'm like, oh, I see why this is a problem.
So many years ago, I read somewhere that it said that even the two-factor 2FA, there's some way that hacker will able to get the verification code from the text message. I read somewhere many years ago. So they are still able to get the code when it's sent to your phone, right?
Yeah. Well, then you use the Authenticator app that you can get from Sierra College.
Yes, I know the app, but they talk about the code when they send to the message.
What about that on YouTube? Some YouTubers got their accounts broken into, like major accounts have like millions of subscribers that earn like thousands of dollars a day. They got it broken into because the hacker called their phone company. They somehow got their number, called the phone company impersonating the YouTuber, and asked the phone number to be changed or something. And they basically got a hold of their phone number on a different SIM card. And so they basically had their phone. So they were them. And Google couldn't tell otherwise. And so they just got broken because they had
I mean,
access.
security for these high profile accounts just be such a pain to keep track of, because it doesn't take very much for somebody who's persistent enough to piece together all the information they need. Like, let's take that YouTube thing for an example. They might say, they might call up customer service, and the customer says, well, I got some security questions to ask you. What was the name of the pet that you had when you were a kid? Well, so if it's a high profile user, maybe all you have to do is plug into Google, like, what pet did so-and-so own when they were a kid? And maybe in some video they did 5 years ago, they happened to mention the name of the pet that they had when they were a kid. And so you got the answer to that, right? It was just this innocuous, innocent mention of that pet's name, but there it is. There's the answer to that security question. Or you could go to perhaps another website, like you're trying to break into Yahoo, but you go to another website like, I don't know, Yahoo or something like that, and then they ask you some security questions, right? And then all you have to do then is go and Google the answer to those, get into the Yahoo account, and now you got, access to their identity now. And maybe they have the Yahoo account set up as their backup email address for their YouTube account. YouTube, they usually ask you to enter 2 email addresses, a primary one and a backup one, in case the primary one doesn't work. And so now you can get the authentication code sent to your secondary email address, and you can authenticate that way, right? So I guess what I'm getting at is sometimes the way to get in these hackers use is not the direct way in, but this kind of indirect way. Talk to other organizations and other websites and try to piece together enough information that now you can answer those security questions with like authority. Because like, oh yeah, my pet's name was Fluffy. And there's no hesitation on your part because you got that information from somewhere else. Or if you want to get their phone number, maybe all you need is the last 4 digits of their phone number. So you talk to Verizon or T-Mobile, and you somehow get them to tell you the last 4 digits of the phone number. And then now you've got that piece of information, and you can go back to the original one you're trying to break into, right? So it's not just like securing one account. The problem is now more complex, even for ordinary users, to take a broad look at all of the services they subscribe to and make sure, right, that there's, and this is really hard to do for an ordinary person, to like make sure there's no way to piece together your identity out of little snippets that someone can get from a whole bunch of different places. Does that make sense?
There's a really good show about this exact problem where like people use like, not people, it's a Rami Malek, I think, is the main actor. It's called Mr. Robot. It's really popular. But like the first season, he doesn't use any like hacking methods as in like brute force or anything. And he uses like social methods to get a person's like information on what they do, how they like live their online lives. And then you can somewhat get into them, like into their life or into their accounts, just through knowing more about the person and less about
exactly
exact passwords.
And even if it's not hackers doing this, that there are just businesses who that's their job basically, is to piece together information about you from things like your buying habits and where you travel to. And how do they know where you travel to? Well, when you get a credit card, that information is shared with a lot of third-party organizations. The fact that you have a credit card, here's your number, here's your mailing address, your age, right? All that information that you use to obtain that credit card, your social security number, some kind of identification, and then they can do background checks on you. They can run that social security number or your driver's license number, and they contain lots more information about you. And then they can start correlating that information. If they have your credit card number, you go to a gas station and fill up your car. Well, now they know you were at that gas station at that particular time. And then let's say you go to a store and you buy something. And now they know that you were at that store that was near to that gas station at that particular time. And they can start piecing together where you travel during the day. They can probably figure out where you work. Even if you don't buy anything at work, they can figure out where you work just by where you are driving to, where you spend your time during the day. They know where you live. They have your mailing address, of course. They know what kinds of things you like to buy. They can probably analyze videos you've made and posted on YouTube. You know, let's say, you know, I'm on a YouTube video and take a drink of this. Well, now someone knows I like to drink these kinds of drinks. They can display an ad to me. Or they can do facial recognition. They could look at a photograph I posted or a YouTube video that I've posted and see who else is in the video. And now they know I and that other person are probably friends or relatives. And they can scan through all the photographs and YouTube videos on the internet and look for that same face in those other videos and figure out this is that person's identity. They now know, like, let's say it's my daughter's YouTube username, and they know her Instagram name just by scanning through photographs they've found and doing facial recognition. And if they know that I like to drink this, maybe they should deliver those ads to her. Maybe she likes to drink them too. Maybe now that they know they're related, they can start tracking where we go together, where we buy things together. So it's kind of frightening, all the information they can glean out of you just by little snippets here and there.
Especially, like, what's it called? Cookies as well, targeting ads on, like, on websites that you visit.
Yeah. It's like
I've gotten those recently because I was, like, looking at mountain bikes, and I didn't have for like a good year or two, I wasn't really interested in mountain bikes. And then as of late, like a week or so ago, I was looking to buy one. And as soon as I looked up like 3 or 4 mountain bikes on Google and went on their websites, everywhere on YouTube, any place, I just get mountain bike ads.
Yep.
Of just buy our mountain bike or this part or this part. And I'm just out of nowhere. Like this is like an obscure company to me.
Yeah.
Like, 4 weeks ago, but now I know what it is, but it's still giving me like ads for it. So
that happens to me too. And I don't even necessarily do a search for it. Like, I know if I search on Google, then of course Google's going to show me ads, right? But sometimes I'll just go directly to that company's website. Do it, browse around a little bit, look at their products, and then suddenly, like you said, I've got ads for similar products, on Facebook and YouTube. And I'm like, how did they know? Well, clearly that other website loaded a tracking cookie onto my browser, and now
I think on the website use something called a Google AdSense, so they use the Google Ad Network, so they already track you, and then there's also something called a Google Analytics.
Yeah.
So when you come to a website, Google know what is that website about, and then they track how much time you spend on the website. I think I can say that Google know everything.
They probably know more about you than your parents know about you.
And I read somewhere that it's also said that Facebook they read our message. Even though our message should be private. But even though Facebook read our message too, when you talk about a product in Facebook Messenger, and then you go somewhere and then there's a ton of ad about that product show up.
Yeah, I swear my computers are listening to me, because sometimes I've just talked about something with my wife, and I start getting ads for that. Like we weren't even on, like, we weren't talking into the computer, but I swear that thing's listening to us. I mean, I'm pretty sure it's not. It's just a coincidence. Like, maybe the fact that I was mentioning that to my wife means that I probably maybe browsed for it a couple days ago inadvertently, or I passed by that store and it knows that I passed by that store because I made some purchases around that store. You know, so they can piece together that information and just kind of figure out what's on your mind, just based upon where you drive, where you make your purchases, and what things you search for.
So side note, this isn't like related to anything. I've noticed that you have like very mechanical sounding switches on your keyboard. And I'm like wondering if you have like an old IBM
Me?
keyboard that you use.
Me?
Yeah.
No, it's just my laptop keyboard.
Really?
Yeah, nothing special.
Are you into keyboards or no? I feel like you would be.
Yeah, actually, I mean, I don't put up with mushy keyboards for very long. So I used to own some of those really nice ones, those really loud, annoying clicking ones. But they were too loud, so I eventually got rid of those. But yeah, I used to be into those. But that's definitely something that I consider when I buy a computer. The keyboard has to be pretty nice. But seriously, that's just when maybe my microphone just picks up the noise because it's just, I mean, the microphone's there, right? And the
That's really
keyboard is
good.
just a few inches
Yeah.
from that. Well, let's talk about lab number 7, which is the last, one of the last Python assignments. And there's really not a whole lot of programming to do with this one, but you're going to kind of do on a smaller scale what hashcat does 55 billion times per second. So there's 2 files to download for this. There's lesson 8 and lab number 7. So I'm going to download both of those. And then we'll upload those 2 files. Let me refresh the screen here again. I let it sit idle again too long. There we go. Okay, lesson 8. Learn how to use hashes in Python. I've already shown you this a little bit. So you're going to import the hash library, and in particular, we're going to use MD5. And the only reason for using MD5 is because the hashes are nice and short, and they're easy to look at. If you use the other ones, they're just long, right? So just realize that these days, because the hashes on MD5s are short, MD5 is not used so much for doing things like storing passwords. It's still used these days for checking to make sure that a file or a document hasn't been corrupted somehow, but it's not used to store passwords anymore because the hashes are so short, and because actually, astonishingly enough, researchers have found a couple of vulnerabilities in MD5 where the distribution of the hashes across all possible inputs is not uniform. There actually are some spikes in a few places where some of the hashes are more prevalent. And so you can actually, in less time than brute force time, for a given document, a given input, you could find another input that has the same hash. So they recommend don't use MD5 anymore for doing things like securely storing passwords, but it's still fine for checking document integrity. We're going to use it because, again, the hashes are nice and short. The MD5 algorithm itself is fast. Just realize that if you were to do this for real, on a real system, you would use SHA 256 or 512. The hashes are just bigger. So go ahead and import that library. And then, of course, when you hash something, you need to use the .hexdigest method on there to get this hexadecimal number. And it's actually just a string. You notice there's quote marks around it. The reason for that is that a hexadecimal number has letters in it, and so because it has letters, it's not technically a base 10 number. So there's quotes around it. Anytime you type in a hexadecimal number in this assignment, remember to put quotes around it. Anytime you type in a string, a plain text string, it needs to be a byte string, so put a B in front of it. So try it out yourself. You can replace your string here with anything you want. You can hash things pretty quickly, pretty easily in Python. So problem number 1 is to hash each one of these strings and assign it to these 3 variables. So you're going to have to open up, actually there's a couple ways you can do it. You can open up a new cell and then you can just hash each one of those strings. You could use this cell up here if you wanted to, and then just assign to each one of these variables the resulting hash. Or you could do something like salad equals MD5 and then put in fruit salad dot hex digest, and then whatever the hex digest method returns, that'll be the value that gets assigned to the variable. So there's no need to actually see the resulting hash. You're just going to assign to the variable what that hash is, and then down below here it'll check to make sure you got it right. Now I had to obfuscate or hide the actual hash so that you couldn't just copy and paste the answer into the box above. I guess what I'm essentially doing here is I'm computing a checksum of the hash, and then I just make sure that checksum worked out okay, and then I assume the hash is probably correct. So you can run this cell down here just to check your answer. So there's 2 ways to do this. You could paste in the actual hash itself, or you can just type in the code that would generate the hash and then put that in there. Problem number 2. I've hashed 2 of these 6 words, and here are those hashes. Try to figure out which 2 words they are, and then assign to these 2 variables, mystery1 and mystery2, the plain text words. Remember, they have to be byte strings, so put the B in front of them. So you need to figure out which 2 of these 6 words give you these hashes, and then assign to these variables the answers to that. So think about how you would do that, and then go ahead and do it. And somebody asked, what is Jupyter Hub? So Jupyter is a Python programming environment that uses something called a Python notebook, where you can intersperse text and Python code very easily. You can actually download Jupyter to run on your own computer. You just go to, I think it's jupyter.org with a Y, jupyter.org, and there's instructions there on how to download Jupyter and run it on your computer, and then you can try out this assignment yourself. Okay, again, this cell down here checks your answer. It computes some checksums of the hashes, and then checks to see if the checksums match. Okay, problem number 3. Here's a hash. I can tell you that it was produced by taking 3 letters, a 3-letter word. Actually, it's not even a word. It's just 3 letters, and putting them together and then hashing that. So here is a little function called brute force 3 that has inside of it 3 loops. Loop C1, C2, and C3 that each loop over this alphabet. So C1, C2, and C3 each contain a single character. Then inside the loop, we're going to concatenate those characters together. We're going to put them together to construct a word. Then we're going to take that word, run it through the MD5 algorithm, produce a hex digest, and then see if that's equal to the target, which we passed in as a parameter. So we're going to pass in, we're going to call brute force 3 with a hash that we want to crack. And then it's going to brute force it by running through all the 3-letter combinations and then seeing which one is those hash to be the same hash value that we're trying to crack. And if it finds that hash value, it just returns what the plain text word is. So paste in the hash that you want to crack, which is this one up here. Remember to put it inside quotes. And then run the brute force 3 function, and a few moments later it should produce the answer. And then paste your answer right here. And then you can check your answer in the cell below. So you won't end up with a word, you'll end up with just some random 3-letter combination, and then you'll paste that answer in and check it. So problem number 4, write a function called brute force 5 that attempts to crack this hash. This hash is composed of 5 letters that have been concatenated together to produce a word. So you'll have to write your own brute force 5 function in order to crack this password. Now, the big hint is I've written for you a function called brute force 3. You're going to write one called brute force 5 that loops across 5 letters. So you're going to construct it in much the same way, except that instead of 3 loops, it's going to have 5 loops in it. Remember to indent, right? All these statements to check to construct the word, and then check to see if the word is equal to the target, are contained within the innermost loop. So if you copy and paste this brute force 3 and then attempt to modify it, remember to adjust the indentation of the statements that are inside the inner loop so that they match. Okay, here's another way to do problem number 2. Remember problem number 2, I had a list of 6 words and a couple of hashes, and you wanted to figure out which of those 6 words have been hashed to match. Well, another way to do it is, instead of just kind of like trying it by experimentation, you could construct a list of all the possible words it could be. Here's 6 possible words it could be. And then it will loop across that list of words, hash each word, see if it's equal to the target hash, which you passed in, and then return the word that matches. For the brute force 3 and brute force 5, yes, you could use recursion to do this. However, I already showed my students a technique earlier in the semester when they were running through all the combinations of some binary values to produce truth tables. It was constructed in much the same way. So I'm kind of leveraging that pre-existing knowledge about how to construct those loops to do this one. Okay, so that's lesson 8. Now we'll move on to the actual assignment itself. Oh, I see a typo here. This is actually lab 7, but in here I said lab 6. This is actually lab 7. So you've learned about the RockU file. It contains 14 million passwords. We can't store all those passwords into our notebook. It would just be too big. So what I've done is I've pulled out the first 300 entries out of that list. So this cell here creates an array called RockU that contains in it the first 300 words out of that RockU list. So just go ahead and execute this cell, and it will create that array. You can inspect the contents of it with this cell here. You can see that there are 300 byte strings in there. So we're going to crack some hashes using these 300 words. Problem number 1. Write a function called crack1. It takes a hash as a string, the target that you want to crack, and it returns the matching word. The function should loop through the RockU array, hashing each word in turn. If the hash matches the target, go ahead and return it. For example, if I pass in hash 0, which is this one down here, it should return computer as the plain text. So I've already given you the answer to the first one. So once you've cracked all 3 hashes, you're just going to call the crack1 function 3 different times with different hashes. then you should assign to the variables word1, word2, and 3 with the plain text passwords that those correspond to. So right here, write the crack1 function, and then in the cell below, assign these 3 variables. And then you can check your answers right here. Okay, if you can't figure out how to do this problem, take a look at the lesson. Right here at the lesson, we had a list of words, and then we wrote a function that would figure out which word in that list was the password that you want to crack. Problem number 2. In this problem, the computer has randomly picked 2 words, I think, 10 words out of the RockU file. It hashed them and then assigned them to a variable called random hashes1, and it also did the same thing for random hashes2. And then hashes3 also contains 4 hashes that correspond to 4 words out of that RockU array. Okay, so in this case, we don't know what those hashes are. Up here, in problem number 1, we know what the hashes are. Here they are. Here's the 4. But in problem number 2, we don't know which 10 it picked. So randomly picked 10 words out of the RockU file, it hashed all of them, and then it threw them all into an array, and then it says, okay, go ahead and crack those. So you're going to write a function called crackList that takes a list of hashes to crack and returns a list of cracked passwords. So the big hint here is we already have a function that takes in a single hash and returns to you a single plain text password. Now we want to write a function that takes a list of passwords and returns a list of cracked passwords. Let me say that again. We want to write a function that takes a list of hashes and produces a list of plain text passwords. So we already have one that can take 1 hash and produce 1 plain text password. And now we want to write a function that takes a list of hashes and produces a list of plain text passwords. Map that function onto the list of hashes, and you should be able to crack all of these hashes very quickly. So try it on those 3 different lists. You got hashes3, random hashes1, and random hashes2. Problem number 3. The variables hash4 and hash5 contain 2 mystery hashes. They are constructed by taking a word from the RockU list and appending a single digit onto the end. You know, for example, Morgan 3 or Shadow 7. Write a function that solves this problem for you. Here are 2 hashes. They are constructed by a word from the RockU list followed by a single digit. Here's a list of digits you can use. So you don't have to construct your own. You can use the one that I gave you. Write your function here. Write this function that you can call it whatever you want. And then figure out what those 2 hashes correspond to. Remember, they consist of a list out of the RockU file or the RockU list followed by a single digit. So you're going to concatenate these 2 things together to construct a new candidate password and then hash it, see if it matches, and then return it if it does. Paste your answers here and then check it with a cell down at the bottom. And that's it. So you have just done on a small scale what hashcat does with a GPU, right? To give you some idea about what hashcat is actually doing behind the scenes. It's really nothing more complicated than this. So that's it for the assignment. I still keep promising the people on YouTube I will figure out a way, probably some kind of Dropbox somewhere where I can put these files and then you can try them out on your own. It's up to you to figure out how to install Jupyter, but you can do it pretty easily if you go to jupyter.org. If you already have Python installed on your computer, then it just be, maybe it's just as easy as saying pip install Jupyter Lab or pip install notebook. And then it's up and running. If you're using something like Visual Studio Code, let me create a new window here. Then you can go to extensions. You can install the Python extension right here. And that will also include Jupyter as well. And then you can just load your notebook files and it will open them up inside of Jupyter. So that may be an easy way to get things going as well. Any questions? So we ran through that pretty quickly, but if you watch the video, you can just go back and pause it when you need to. And I hope you get something out of this, right? I hope you get something out of the assignment. I hope you have fun with it, right? It's kind of neat to see your program just suddenly, boop, out comes the answer, right? It's really cool to see that. And then this will be one of the last Python assignments we do. In fact, I think this is the last one where you actually have to write your own programs. There's one more assignment that uses Python, but we're just using it as a calculator in that case. So there's not much to do.
So will the rest of the class be less based on programming, or are we going to just switch to a different language?
We'll do more problem solving, right? So when you do things like combinations or permutations, you'll be working out some of those problems like with a calculator, or you could use Python to do those as well, but there's no explicit Python programming. We'll be learning how to do things like graph algorithms, and again, those will be ones where you just work it out on pen and paper. So we were really learning the Python to kind of end up here, doing RSA and doing the hashing. But notice how we're putting together all those concepts we learned, like filter, map, functions, lists, loops, all those stuff that we learned over the past few weeks come together to make these past two assignments. Somebody said, could we do this for the C class? Yes, actually the C class we will be doing the password cracking as well, but we'll be doing it in C instead of in Python. And because we have a few more resources at our disposal, we'll be able to use, not the entire RockU file, but we'll be able to use one that has 2 or 3 million entries in it and load that up into memory and then use that to crack passwords. How can I write big math expressions and also solve instantly? I don't understand that question. I mean, in Python, it uses large integers just natively, right? So you can throw at it an expression that results in a large number, and it just handles it, right? It just basically stores the number as an array of digits rather than as a binary number. But in Java, you have to use a library. There's the big integer library that you can use to load in big numbers. The downside of using that library is in Java, you can't use the standard operators. You can't use like plus to add things together. You have to call the add method. And if you want to divide, you have to call the divide method. Right? So the expressions that you type in no longer look like standard mathematical expressions. Now they just look like a sequence of method calls. So it gets a little unwieldy, but that's a limitation of Java. C++, you can do this as well. It's got an equivalent library that you can import or include into C++ and then get use of big integers. And then you can use the operators. You can just use plus and divide like you normally would, because C++ allows operator overloading. You can have an operator like plus mean different things in different contexts. In Java, you can't do that. Java has a very limited set of operator overloading, and they're all just the built-in operator overloading. Like plus can be used to either join strings together or it can be used to add numbers together, but that's all built into the language, right? It's not something that you, the programmer, can actually make your own operators like you can in C++. Oh, you mean do the image recovery assignment in a Dropbox link? Yeah, I'll think about that one as well. Yeah, maybe I'll somehow get them all in the same places. So I don't know, maybe by this weekend I'll have something cooked up where you can do that. Okay, if there's no other questions, then why don't we call it a day? If you're following along in my C class, I'm not going to have that tomorrow. I am doing interviews for a full-time position at our institution, so I will not have the live stream tomorrow for the C class. Okay, I will say goodbye to the Zoom folks. Have fun with this assignment. And the next time we see Python, we will also have fun with that assignment. That'll be regular expressions, which we'll do in a few weeks. All right, take care. Have a good weekend. I will see you later. Bye-bye. Let's see. Next week we're doing sets on Monday, and then I think it's combinations and permutations on Wednesday. And then the week after that, we get into discrete probability. That'll take, I think, it's either 2 sessions or 3 sessions to get through that. And we'll end up learning how spam filters work. And then following that, I think we get into graph algorithms, if I'm not mistaken. Again, we'll spend a couple of weeks on that. We'll learn about shortest path, minimum spanning tree, maybe we'll have time to do A star. And then we get into finite state machines, and that takes about 3 weeks to get through. So we got 1 week, 2 weeks on that, and then another 3 weeks. So that's 6 right there. And then we have 1 week where I have kind of like nothing scheduled. That's kind of like, if there's nothing, so I put that in there in case someone gets sick or you know, I have something going on, I am able to push the entire schedule back by a week. So we have about a 1 week, a week and a half where we got nothing scheduled. And then finally the very last week is finals week, where I meet with all of my students and go over their assignments for the semester. So that's the rest of the semester. Will passwords even exist in the next decade? I have no idea. I kind of hope not. Because they're just going to be a pain to type in, right? I don't know what's gonna come up in the next decade. You know, passwords have been around for 4, 5 decades already, so I can't see them going away in the near future. But I also can't see them lasting very much longer because they're just getting unwieldy. Well, why don't we, I got some work to do, so hey, it was great seeing you. And I hope you had fun today. I hope you learned something. Hope you're gonna go try out hashcat yourself. Try to crack some hashes. If you download hashcat, it comes with some files that you can play with. So in there is, what do we got here? We got example 0, which are MD5 hashes. You've got example 400, the example 5, example 500. And those are all different kinds of hashes. Let's take a look at example 0. So those are all MD5s. I can tell those are MD5s by just how long they are. They're 32 characters, 128 bits. Those are MD5s. Oh, there's only one in here. And this is a, I'm guessing this is, oh gosh. So for here, when this kind of hash, this first character, or these first couple of characters in between the dollar signs up front, tells you what kind of hash it is. And so the capital H, maybe this is an HMAC hash? And then this one here, the $1, I think that means this is an MD5 as well. No, but this is a salted one. So this is MD5. Here's the salt. And then here's the hash, but it's been encoded, I think, in base 64. But anyway, there's an attack mode for dealing with this style of hash as well. Is it possible to crack a password of a pen drive whose password is forgotten? Yeah. So somewhere on that pen drive is the hash. Well, actually, no. Actually, you may not be able to. If it's encrypted, then well, the answer is yes, you could eventually do it, but you have to guess what the key is. That's going to be tough. Because it probably uses something like AES 256 to encrypt all the contents. And to be able to decrypt it, you need to know what the password is. So that's going to be a lot tougher to do. It may be possible. You could still do something like a dictionary attack where you try words, or if it's a pen drive that you created, you probably have some idea what the password is. Like you might know that when I encrypted it, I probably used a word and maybe stuck some digits on the end or put a symbol in there. That actually happened to me not too long ago. My son had forgotten his Windows admin password on his computer. And no, I'm sorry. It was my son's computer. I set up the admin account and I forgot what the password was. That's what happened. I followed some instructions I found on the internet for obtaining the hash. You can basically pull the hard drive out of the computer, attach it to another computer, and then find the file that contains the password hash on it. And there's some instructions on the internet about how to do this. Once I had that hash, I then fired up this GPU server, $1.50 an hour, plugged in the hash, and then I plugged in a pattern. Since I set it up, I kind of had an idea about what the password would look like. It'd probably be like a word with a digit or a symbol stuck on the end. I just didn't remember what the word was. I didn't remember how I'd capitalized it, and I didn't remember what the symbol or the digit was on the end. So there wasn't actually that much for it to try. So I just typed into hashcat what I thought the pattern was, right? 6 or 7 letters followed by a number or a symbol, and I just had it go at it. And it only took a few minutes for it to finally pop out with the answer. And when I looked at it, I went, oh yeah, of course that was the password. I should have tried that first. But it was good that it was good practice, right, to just try this out and crack that Windows password. So there's not going to be a hash on that pen drive. I presume it's an encrypted like file vault type thing. And in that case, in order to decrypt it, you need to know what the password is. Presumably when you go and load that pen drive in the computer, it up pops a box that says, please enter the password. And that is the password that is used to decrypt the contents of that disk drive. And if you don't have that password, it's not going to work. Now, it's possible, I would say there's a slim possibility that that's not the way it works. It's not the password itself that you type in that is the decryption password. It could be that the decryption password itself is stored in a file on the pen drive. But there's an encryption on it as well. And so when it pops up with a box asking you to type in a password, it's basically going to determine whether or not you have access to that file. So it could do something like taking your password, hash it, check to see if it matches a hash that's already on the pen drive, and then if those match, then it lets you see lets it load in the contents of that file that contains the actual AES password. In that case, maybe it might be possible to do, but I would have no idea where that hash is stored. You'd have to Google around and find out if somebody else has done this before. But my guess is it's not stored on the pen drive. It's all encrypted, and the password you type into that box is the decryption password. And in that case, nothing is stored on that pen drive that'll give you access to it by cracking anything. You're just going to have to brute force it. And you know, there might be a program out there that can do that. That can just brute force passwords, try each one of them, and then see which one of them happens to unlock the files. But other than that, I don't have a whole lot of help for you. All right, well, why don't we end this here? I will see you next week. I hope you have a great weekend. And take care. Be safe. Bye-bye.